Skyglow is the diffuse luminance of the night sky. Apart from discrete light sources such as the moon and visible individual stars, it is a commonly noticed aspect of light pollution. Although usually referring to sky luminance arising from the use of artificial lighting, skyglow can also refer to all diffuse sources of night sky luminance, including artificial as well as natural sources of diffuse nighttime light like the zodiacal light, starlight, and airglow. In the context of light pollution, skyglow arises from the use of artificial light sources, including electrical lighting used for illumination and advertisement, and from gas flares, light propagating into the atmosphere directly from upward-directed or incompletely shielded sources, or after reflection from the ground or other surfaces is partially scattered back toward the ground, producing a diffuse glow that can be seen from large distances. Skyglow from artificial lights is most often noticed as a glowing dome of light over cities and towns, yet is pervasive throughout the developed world. Causes: light used for all purposes in the outdoor environment contributes to skyglow by sometimes avoidable aspects such as poor shielding of fixtures, and through at least partially unavoidable aspects such as unshielded signage and reflection from intentionally illuminated surfaces. Some of this light is then scattered in the atmosphere back toward the ground by molecules and aerosols and clouds, causing skyglow. Research indicates that when viewed from nearby, about half of skyglow arises from direct upward emissions and half from reflected, though the ratio varies depending on details of lighting fixtures and usage, and distance of the observation point from the light source. In most communities, direct upward emission averages about 10% to 15%. Fully shielded lighting decreases skyglow by about half when viewed nearby, but by much greater factors when viewed from a distance. Skyglow is significantly amplified by the presence of snow, and within and near urban areas when clouds are present. In remote areas, snow brightens the sky, but clouds make the sky darker. Mechanism: there are two kinds of light scattering that lead to skyglow: scattering from molecules such as N2 and O2, and that from aerosols, described by me theory. Rayleigh scattering is much stronger for short wavelength light, while scattering from aerosols is less affected by wavelength. Rayleigh scattering makes the sky appear blue in the daytime. The more aerosols there are, the less blue or whiter the sky appears. In many areas, most particularly in urban areas, aerosol scattering dominates, due to the heavy aerosol loading caused by modern industrial activity, power generation, farming and transportation. Despite the strong wavelength dependence of Rayleigh scattering, its effect on skyglow for real light sources is small. Though the shorter wavelengths suffer increased scattering, this increased scattering also gives rise to increased extinction. The effects approximately balance when the observation point is near the light source. The human visual perception of skyglow, generally the assumed context under discussions of skyglow. Sources rich in shorter wavelengths produce brighter skyglow, but for a different reason: measurement. Amateur astronomers have used the Bortle dark sky scale to measure skyglow ever since it was published in Sky and Amp Telescope magazine in February 2001. The scale rates the darkness of the night sky inhibited by skyglow with 9 classes and provides a detailed description of each position on the scale. Amateurs also increasingly use sky quality meters that measure in astronomical photometric units of magnitudes per square arcsecond. Professional astronomers and light pollution researchers use various measures of luminous or radiant intensity per unit area, such as Lambert's, magnitudes per square arcsecond, or candela per square meter. Dependence on distance from source. For relatively small distances between the light source and observer, the intensity of the skyglow contribution from a single source of light is inversely proportional to the distance between the source and the observer. This can be understood as follows. The illumination of any portion of atmosphere visible by the observer falls as 1r2, but the path length of illuminated air along any given line of sight which is illuminated comparably to the brightest illumination grows linearly with distance together. This gives a 1r dependence. This is valid when the distance between the source and observer is smaller than the scale height of the atmosphere. At distances much larger, where the path length of illuminated air is limited by the height of the atmosphere itself, this becomes an inverse square dependence. Dependence on light source. Different light sources produce differing amounts of visual skyglow. The dominant effect arises from the Perkin shift, and not as commonly claimed from Rayleigh scattering of short wavelengths. When observing the night sky, even from moderately light-polluted areas, the eye becomes nearly a completely dark adapted scotopic. The scotopic eye is much more sensitive to blue and green light, and much less sensitive to yellow and red light than the photopic eye. Predominantly because of this effect, white light sources such as metal halide, fluorescent, or white lead can produce as much as 3.3 times the visual skyglow brightness of the currently most common high-pressure sodium lamp, and up to 8 times the brightness of low-pressure sodium or amber aluminium gallium indium phosphide lead. In detail, the effects are complex, depending both on the distance from the source as well as the viewing direction in the night sky, but the basic results of recent research are unambiguous. Assuming equal luminous flux and matched optical characteristics of the fixtures, white sources rich in shorter wavelengths produce dramatically greater skyglow than sources with little blue and green. The effect of Rayleigh scattering on skyglow is very small. Much discussion in the lighting industry and even by some dark sky advocacy organizations of the skyglow consequences of replacing the currently prevalent high-pressure sodium roadway lighting systems with white LEDs neglects critical issues of human visual spectral sensitivity, or focuses exclusively on white LED light sources, or focuses concerns narrowly on the blue portion of the spectrum. All of these deficiencies lead to the incorrect conclusion that increases in skyglow brightness arising from the change in light source spectrum are minimal, or that light pollution regulations that limit the circuit of white LEDs to so-called warm white will prevent skyglow increases. Improved efficiency can allow designers to lower lighting amounts, but efficiency improvements sufficient to overcome skyglow doubling or tripling arising from a switch to even warm white LED from high-pressure sodium has not been demonstrated. Negative effects. Skyglow, and more generally light pollution, has various negative effects, from aesthetic diminishment of the beauty of a star-filled sky, through energy and resources wasted in the production of excessive or uncontrolled lighting, to impacts on birds and other biological systems, including humans. Skyglow is a prime problem for astronomers, because it reduces contrast in the night sky to the extent where it may become impossible to see all but the brightest stars. Many nocturnal organisms are believed to navigate using the polarization signal of scattered moonlight. Because skyglow is mostly unpolarized, it can swamp the weaker signal from the moon, making this type of navigation impossible. Due to skyglow, people who live in a near-urban area see thousands fewer stars than in an unpolluted sky, and commonly cannot see the Milky Way. Fainter sights like the zodiacal light and Andromeda galaxy are nearly impossible to discern even with telescopes. Effects on the ecosystem. The effects of skyglow in relation to the ecosystem have observed to be detrimental to a variety of different organisms. The lives of plants and animals alike are affected as the natural environment becomes subjected to unnatural change. It can be assumed that the rate of human development technology exceeds the rate of non-human natural adaptability to their environment. Therefore, organisms such as plants and animals are unable to keep up and can suffer as the consequences. Although skyglow can be the result of a natural occurrence, the presence of artificial skyglow has become a detrimental problem as urbanization continues to flourish. The effects of urbanization, commercialization, and consumerism are the result of human development. These developments in turn have ecological consequences. For example, lighted fishing fleets, offshore oil platforms, and cruise ships all bring the disruption of artificial night lighting to the world's oceans. Similar problems of disrupting the environment and its biosphere are also very prevalent in regards to energy resources such as the installation of wind turbines and the interference they cause with not only bird flight paths, but also with human neurology. As a whole, these effects derive from changes in orientation, disorientation, or misorientation, and attraction or repulsion from the altered light environment, which in turn may affect foraging, reproduction, migration, and communication. These changes can even result in the death of certain species such as certain migratory birds, sea creatures, and nocturnal predators. Besides the effect on animals, crops and trees are also very susceptible in being destroyed. The constant exposure to light has an impact of the photosynthesis of a plant, as a plant needs a balance of both sun and darkness in order for it to properly survive. In turn, the effects of skyglow can affect the production and rate of agriculture, especially in regards to farming areas that are close to large city centers.